And I was successful this morning, finally found some new markers, so we're doing a little better now. Alright, so Riemann sums. So there's quite a few pages within this section. It's still allotted that we should be able to finish it in about 2 days. It may take 2.5, so it might be finished Monday. We'll have to see. There's like 9 pages, but each one is like one example because there's a lot of room for them. So we're going to try to go through them at a decent pace. Try to get through as many as we can today. In calculus, the result of the integral of f of x dx is a function that represents the antiderivatives of the function f of x. This is also sometimes referred to as an indefinite integral. The result of the integral from a to b, so those are bounds, of f of x dx is a value that represents the area of the region bounded by the curve and the x-axis on the interval from a to b. So they're saying when you take the integral from a to b, any area under that curve from the x-axis to where that curve is, when you take the integral, you're actually finding the area underneath that curve. Calculating Riemann sums is a way to estimate. Again, this is just estimating. You're not getting the exact value. Estimating the area under the curve. The value of the integral from a to b of f of x dx for a graphed function on a particular interval. In this activity, you will learn to calculate 4 types of Riemann sums. We're going to have left-hand sums, right-hand, midpoint, and trapezoidal sums. So we're first going to focus on the left and the right, and we may make it to the midpoint today, I'm not sure, but we're definitely going to do left and right today. So approximation number 1, left-hand Riemann sum with intervals of length 2 units. So looking at the picture down here, what we're trying to do, an integral, is finding the area underneath this curve that's bounded by the x-axis. So everything from the x-axis to the curve. That's what we're trying to do, is find the area underneath. So it says, let's consider for a moment the function f of x. This function is graphed below. On the interval from 1 to 7, subdivide the area bounded by the graph of the function and the x-axis into rectangles of length 2. Place the upper left-hand vertex of the rectangle on the curve each time. Then calculate the area of each rectangle and sum the areas to approximate the area of the region under the curve bounded by f of x equals negative 1/3 x squared plus 2x plus 5, where x is equal to 1, x equal to 7, and the x-axis are the bounds. Okay? So what we're going to start. From 1 to 7 is the interval, so I'm just marking these so you can tell where we're starting. We want to go from 1 to 7, so those are going to be our bounds, and the x-axis. In this case, they're telling us Riemann sums are all, we're going to use rectangles to help us estimate. So they're telling us in this example, we want 2 units for our rectangles. So our rectangle, the first one, is going to start at 1 and go all the way up to the curve. And again, this is a left-hand sum. So on the left side of your rectangle, that's where it stops on the curve. And again, these rectangles are 2 units. So we go over 2 and back down. So this is the first rectangle that we're going to try to find the area of. The next rectangle, well, it starts right here. It's going to go up. The left side of the rectangle you take all the way to the curve and then go over 2 units. Go back down. So again, this is our next rectangle. We're going all the way to 7 though, so we still need one more rectangle. So again, take this rectangle up till you hit the curve. On the left-hand side of this rectangle is where you hit the curve. So visually, right now, can we see why these rectangles only approximate the curve? Over here, we have some area that wasn't touched by our rectangle. And over here, we have some areas that are overestimating because they're over that line. So this is why it's an approximation. It's going to get us close to what this area is, but there's a little bit here left out and a little bit here that was overcompensation. So it's going to be close. So what we're doing is we're taking an integral from 1 to 7, those are our bounds, of f of x dx. And again, this is an approximation, so we're not using an equal sign, it's an approximation. Now what they want us to do, they said, we calculate the area of the rectangles, and that will tell us an estimate of our integral. Well, how we're going to do this? We have a function. And we know, since we're doing a left-hand rule, that this point is on the line right here, or on our function. So we can calculate, this was 1, f of 1. So we can calculate f of 1. But the units for this rectangle, remember, were 2. So we have to multiply whatever f of 1 is, we have to multiply that by 2. That will give us the estimation of the area for the first rectangle. But we have 2 more rectangles. So now this rectangle, it's on the curve at f of 3. So we can approximate, or we can get the value of f of 3, because we know we're on the curve at that point. But again, this is 2 units wide, so we need to multiply that by 2 to find the area of this rectangle. And then we have 1 rectangle left. So plus, again, it's going to be 2 because we have the 2 units. This one is 5. We know we are on the curve at f of 5. So we can pull a 2 out of all of those and calculate f of 1 plus f of 3 plus f of 5, and we can get an estimate. So you need to calculate f of 1, get a value, add f of 3, add f of 5, and multiply by 2, and we can have an estimate of what's under the curve. So take a moment, use your calculators, find what our estimate is under the curve. And we don't really have any units, so just find a value, and let's go to 3 decimal places. Somebody gets an answer, let me know. We'll write it down. Yeah, 42.667. That is our approximation under that curve. So now visually we need to think about what we just did. Looking at our rectangles, looking at the curve, do you think that's an underestimation or an overestimation? Daniel?
Probably an over.
Yeah, we can see we have this portion here that was missed, but we have this portion that was over and this larger portion that was over. So if we tried to fill that in, we're still going to be over. So this is an overestimation. An overestimation. Because if you actually think about it, you can look at your blocks you have in your grid. There's 1, there's like a half, and there's little pieces. Well, we have 1 here. That makes another 1, plus almost another one there, another one there. So it's going to be a little bit of an overestimation. All right, I know it's just the first one, but are we okay? We're going to have lots more practice with this. All right, so we're going to do, I think we have we have 2 more left-handed sums. So as we go to the next page, we have 2 on here. Let's focus on approximation number 2. So again, a left-hand Riemann sum with intervals of length 1 unit. So this time 1 unit, not 2. They're still left-handed. Interval 1 to 7, so that hasn't changed. We're dealing with the same function. So same function, same interval, we're just using a different way to approximate it to see if we can get closer to the actual value of the area underneath. So we start at 1 and go up to that value. But again, we're only 1 unit wide this time. So we're going to have a lot more rectangles. So drawing all my rectangles, this is just visually showing us what we're trying to find the area of. Again, on the left side of each rectangle, you should be on the curve, on the left side of each rectangle. Are we good with the rectangles? All right, let's start to actually create the integral then. So we know we're still integrating from 1 to 7 of f of x dx. And again, not equals, sorry about that, approximate. So think about what we just did in the first one. The units were too wide, and we had that 2 we pulled out. So what are we going to have out in front of everything for this problem? Just a 1. Yep. Well, we need to calculate f of 1 plus f of 2 plus f of 3, f of 4, f of 5, and f of 6. So all of the spots where you have a dot on the line is where you need to calculate. Again, you have some of those from the previous problem. If you don't want to recalculate some of those answers, you don't have to. But plug it into your calculator and let's find the estimation. So f of 1, f of 2, 3, 4, 5, and 6, and all of those need added together to find the estimation of the area under the curve. Again, each one of these values are just where you have a dot on the left-hand side of the rectangle. Which part are you looking at?
Draw another rectangle.
So, if you look at your values, I know they're hard to see here. This is an 8 right here. So up here it says we're going from 1 to 7. The interval from 1 to 7. So we started at 1 and we ended at 7. I know those values are hard to see, but this is 1, 2, 3, 4, 5, 6, 7. So we're trying to find the area from 1 to 7 bounded by the x-axis. Okay? Does that help out, Ariana?
Yeah.
So if they said 1 to 8, yes, we would include one more.
Okay.
But the 1 and the 7, that's where we're stopping. Those are our bounds. Did anybody find a value? It should be similar to what we had before, but it should be a little different. But it should be close, because we're still estimating it. Go ahead.
41.668.
Okay, I think I had, very close, I had 667. 41.667, or 68. Okay, so think about how we drew these rectangles and what we calculated. Do you think this is an overestimation or an underestimation? I think it's still an over. We have a small piece there and there, but then we have this piece, this piece, this piece, and this piece. If we add those all together, that's more than enough to take care of those empty spaces. So again, this is an overestimation. So what we're doing so far with both examples, we found the area of each rectangle, and we're just adding the area of the rectangles together. An estimation of the integral. So if you want to go ahead and start the next one, the approximation number 3 is left hand, so nothing's changed yet except the interval. So now the interval is only 1/2, so there's going to be a lot more rectangles. So go ahead and start drawing all of those. It's going to be a lot harder to draw because there's going to be so many of them. Again, I know it looks a little messy up here, but there's a lot more squares or rectangles, so we're trying to find the area within all of those. Okay, again, we have all of these left-hand sides of each of the rectangles are on the curve. So again, the same problem, we're trying to estimate the integral from 1 to 7 of f of x dx. And again, think about what we're doing. We're finding the area of each square, so a base times a height or a length times a width. So the length now of these are what? What's the unit? 1/2. So the number out in front this time is a 1/2 because that's how wide they are. Now we're going to multiply by each of their heights. So that's the f of 1. And this time we're going to go from f of 1, what's the next one?
6.5.
Well, to 6.5, yes, that's our last one. So we're going to go in half increments. So I'm not going to write them all down to save some space. F of 1 plus f of 1.5 plus f of 2 plus dot 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 f of 6.5. Again, I got the pattern down so I know what I'm looking for. But now I need to actually go ahead and calculate that. The 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, all the way to 6.5, and find that estimation. So that may take a little longer to plug in the calculator. I'll give you some time to do that. All right, any luck out there yet with a value? Anybody get the value? I know this one's a lot more typing. Again, it should be something close to our last two answers because we're still estimating the same curve. Again, it's going to be a little different. So if you get a drastically different answer, maybe you type something in wrong. So it should be similar.
40.91.
Yep. 40.917. again, with the way we drew our rectangles, looking at our pictures, I know it gets harder and harder to tell each time, but do you think this is an over or an underestimate?
Over.
Yeah, it's still going to be a little bit of an overestimation. So it's an overestimate. But as you can realize, flip back to the first problem. Look at your value on the first problem. If you look at the first problem and look at your squares, do you see how much extra space we had with those big squares that we started with, or rectangles? And we had a large value. As we shrunk these down a little bit smaller, our value got a little smaller. Then we made the interval even a little bit smaller, and we got closer. 40. So we went from 42 something to 40.9. So as we make these smaller and smaller and smaller and smaller, there's less overlap. So we're going to get closer and closer and closer to the actual value of the integral. So again, that's why it's an estimation. But as we get these closer and closer and closer together, that estimation is eventually going to come very, very close. Okay? Are we okay with the understanding of the idea behind it? All right, let's go ahead now. We're going to go on to right-hand sums. Did everybody get the last value written down for that one before I moved it? Okay. So right-hand sums. Let's look at the first one together. So approximation number 4 says now we are going to change things up a little bit. On the next 3 approximations, we are going to do a right-hand sum. That is, draw the rectangle so that the upper right-hand vertex of the rectangle is on the curve of the function. Again, we're dealing with the interval from 1 to 7 still, and lengths of 2. So from 1 to 2, or from 1 with units of 2. So the right-hand side of it should be on the curve. So it should look something like that. Again, the right-hand side should now be on the curve. It told us it was length of 2 units. That's why they're 2 wide. And again, we're having the same problem. We're estimating the same problem in many different ways. So we're still doing the integral from 1 to 7 of f of x dx. What's my coefficient this time? 2, yes, because the width of my rectangle is 2. Now be careful. It's the right-hand side now, so everywhere you have a dot on the line, that's the value you're estimating. So f of 3, f of 5, f of 7. Again, that is estimation, not an equal sign, estimate. So go ahead and find your estimate. Anybody find this value? Daniel, did you happen to find this value?
Yes, I believe it was 34.667.
34.667. So think about what we just found. We had the same problem we've been dealing with the entire class so far, but we did the estimation differently. Visually, if you look at your representation, do you think this is an over or an underestimate? Over or underestimate? It's an underestimate. There's so much area here that we didn't account for, so it's an underestimate. It may be close, but it's still an underestimate. Do you guys feel comfortable trying the next 2 on your own and checking answers? Yes, no?
Yeah.
All right, so again, make sure the right-hand side is on the curve. Follow the same steps we did with the first 3 examples, but again, it's just the right-hand side now. You're going through the same procedure, the same width or length. We started with 2, we're going to go to 1 and then 1/2. So try the next 2, and then we'll check your approximations to make sure they're correct. When somebody finishes approximation number 5, please let me know what you get for an answer. We'll put it up on the board. Again, this time you should be adding up 6 different things. When you get the answer, don't hesitate to let me know what it is.
I'm at 37.64.
Really close. Rounding might have been a little different if you rounded each answer individually before you added them. I had 37.667. So as long as you're within a couple decimal places of that. Visually, look at it. Is this an over or underestimate? Under. Underestimate. I'm going to leave this one up here for a few minutes still if you're still working on it, but if you finished, go ahead and work on the one on the back. Again, it's the continuation of this problem. There are 1/2 intervals now instead of 1. Is anybody having problems with that second problem? I can help you with it. I'm going to walk around, see where everybody's at and how far they're getting. If you get a final answer for approximation number 6, just circle it or put a box around it so I can see it on your page. Take your time. We have some time left, but go ahead and find the approximation of this 1/2 unit. So be careful with this 1/2 one. Remember, we're doing the right-hand side, so you can't start with 1. Your first one's 1.5.
I haven't used the table in so long. Yeah. Is anybody using the table? I've been using it. How do you use something? You wrote down. Is anybody using the table feature? Yes. So, yeah, Benny, everybody, people that are using the table. Okay, that's not good. Yeah. If I figure out how to do that, I'll let you know, but I haven't used that in a very long time, so I'm not sure.
All right, I know if you are still finding the answer, and that's okay. You should get an answer that's close to 38.917, give or take a few decimal places, depending on how you round. 38.917. So go ahead and finish up the work you're on. I'd like to answer 2 questions before we leave, though. So if you're still finishing, that's okay. But if you're done, go ahead and read these 2 questions over here. We're going to answer them before we leave. But go ahead and read those 2. And it's really an idea we've already talked about, if you look at the next 2 questions. Does anybody have a reasoning? We did talk about it. Can somebody explain the first one? Go ahead, Brady.
The approximations get more accurate as the lengths of the rectangular features.
Exactly. The approximations get more accurate. So I'm going to put this up here so everybody can read this. So this is the definitions or explanations you should have. So with the remaining time in class, make sure that you've checked your answer with this one and it's correct, and that you have both of these. So he is completely correct in that it gets more accurate because they get smaller and smaller. And graphically, if you looked at it, well, that's what we did. We looked at it graphically each time. Well, each piece, if you look at the piece that goes over and a piece that's not quite to the curve, each piece, the overage or underage piece, they get smaller and smaller. So as the length gets shorter, those pieces that go over or under get smaller and smaller. So it gets closer and closer to that approximation.